Let's approximate square roots using a very popular rule. It's called Mechanics' rule, and we can actually derive the formula using Newton's method. So we need a function, and it makes sense to actually write a function whose zeros are actually the square roots of the number we're trying to approximate. So with that in mind, let's just take some positive real number a and then define f of x to be x squared minus a. And then, of course, the zeros of f are actually the square roots that we're looking for. Obviously, the positive square root is the one of importance here. And so that would be a nice function to work with in order to move the problem forward. We observe that f prime is just 2x, and now the Newton algorithm, which we used in the last problem, we just need to fill in for the values of f and f prime. So for f of x sub n, we'll substitute x sub n squared minus a, and for f prime of x sub n, we'll just substitute 2 times x sub n. Now, customarily, the mechanics rule is written in a different form other than this. So first, let's just get a common denominator of 2x sub n, and then we notice that we can get some reduction here to an x sub n squared, and then of course the minus minus here gives us a plus a. Now in the literature, the formula is usually written with the 1/2 factored and then the fraction reduced. So we end up with a formulation that looks just like this. That is 1/2 times the quantity x sub n plus a divided by x sub n. And this is our iterative formula, which produces the convergent sequence that we're looking for. Now, as a nice example of this, let's just take a equal to 2. In calculus, we often deal with the square root of 2, certainly with trigonometry. And so what we have here first is to think, okay, if we're interested in approximating the square root of 2, let's use the intermediate value theorem. That's usually the best way to get the ball rolling. So we can observe that f of 1 in this case would just be 1 squared minus 2, which is negative 1, of course less than 0, just using the function f. And then f of 3/2 will just be what? 9/4 minus 2, but of course that's 1/4, which is a positive number. So we have alternation in sign. So by the intermediate value theorem, we know there's at least one c between 1 and 3/2 such that f of c is equal to 0. And that's the 0 that we're interested in. That is the square root of 2. So we can make an initial guess. You can pick a number between 1 and 3/2, and I've chosen 1.3, which is just 13/10. Again, your initial guess is up to you. Do some arithmetic, do some planning, look at how things are spread out when you look at your evaluation of functions. That's completely up to you. Now, when we look at the second iterate, we just go to mechanics rule and replace x sub 1 with 13/10. So we have 1/2 times the quantity 13/10 plus 2 times the reciprocal of 13/10, which is 10/13. And at this point, I just get a common denominator of 130, and this adjusts the numerators. Here, 13 squared will be 169, and of course 20 times 10 is 200. And that will give us 1/2 times 369 when you add these two numbers, divided by 130. So that will give us 369 divided by 260. Now if you divide this out, you get a really nice decimal approximation, 1.41923. Now again, I wrote out, as you see here, 5 decimal places, but our knowledge of the square root of 2 is saying that that's actually a fairly legitimate approximation of the square root of 2. Again, what I've noted here is that we get really fast convergence with Newton's method. It's second order. So you can see here that Newton's method can actually evolve many useful formulas that you can use as a mathematician, scientist, or engineer. And we are done.